Thank you. So I'm project manager Hironori FUDEYASU from Typhoon Science Technology Research Center, Yokohama National University. So I'd like to introduce today our project activity, Typhoon Control Research aiming for a safe and prosperous society. So under Moonshot Goal 8, so as Miyoshi project director, I introduced at the beginning. So our target is a typhoon control research. So we will realize a society safe from the threat of the typhoons by human intervention. So I refer it as a typhoon control, but in reality, it means reducing the typhoon intensity using by the human intervention. It is not truly controlling the typhoons how we want. So we aim to develop the principal fundamental techniques to reduce the typhoon intensity by human intervention through the numerical simulations. So due to the climate change, so a lot of the numerical studies show the increase the typhoon intensity. For example, there is about 10% increase in the maximum wind speeds or 30% increase in the precipitation level. So our goal is to actually reduce the typhoon intensity, so which has increased by climate change to the level that our current infrastructure can manage the damage. So the idea of the typhoon control is not new. So in US, the research on the artificially controlled hurricanes started late 1940s, and Storm Fury, so as Dr. Miyoshi introduced today, so started in 1962. So target of this project is to figure out a way to control hurricanes. So one of the strategy was attempt of weakening hurricanes by flying aircraft into them and cloud seeding. So their report claimed that in the case of the Hurricane Davy, 1969, the hurricane's wind speed reduced by about 30% right after the intervention. So in Japan, there are discussions about whether to research typhoon control. So Basic Act on the Disaster Management 1961 mentioned that efforts should be made to actually regulate typhoons. However, there are many concerns leading Japan to hesitate in engage in typhoon control research. So there are mainly three reasons. So the first, from the scientific point of view, the mechanism of the typhoon was not yet fully understood at that time. So with that understanding, so it was impossible to determine the effect method for typhoon control. So second, verifying the effect of the typhoon intervention. In other words, effect determination was challenging. So we are dealing with a natural phenomena, typhoons or hurricanes. So once we intervene with a typhoon, so we are not able to compare it to the same as a typhoon without the intervention. So the effect determination becomes impossible. The third, LC, even if typhoon control becomes scientifically possible, there is a complex issue of the whether society would accept it or not. But these concerns are from half a century ago. So recent advancement in science technology have led to the breakthrough. For example, so understanding of the typhoon mechanism was improved by extensive past typhoon research. And with our technological advancement and improved observation data, so we are now able to simulate typhoons with great accuracy. And by utilizing the advancement computers and enhanced modeling techniques, we are now capable of quantitatively assess the effective determinations. So currently, these new pieces of the knowledge and technology allow us to research how we actually reduce the typhoon intensity using the numerical simulation. So here is our research organization chart. So we have gathered experts from various fields across Japan as a core research team. So methodological approach, mathematical approach, engineering approach, impact assessment, and LC. So methodological approach is investigating the possible method affecting the typhoon intensity using the numerical simulations. And they are estimating the changes the typhoon intensity and structure due to the intervention level. So mathematical approach is investigating the timing and the location of the effective interventions. So based on the methodological and mathematical approach result, so engineering approach is investigating how to realistically implement the intervention using the device and operations. And also they are evaluating the quantity and cost of the device, so required to affect the change in the typhoons. So meanwhile, impact assessment is estimating the benefit to human associated if typhoon intervention successfully weaken the typhoons in terms of the typhoon damage. So LC is organizing the intervention method and benefit cost to establish the roadmap and action plan. So here is an overview of the intervention method for typhoons being considered so far. So candidate methods are summarized in this schematic diagram, changing the convective cloud by seeding, so reducing the sea surface temperature and evaporation from the sea surface, and the changing wind speed, temperature, humidity near the sea surface by fountain, unmanned ships, barriers, and windbreak nets. So today, I'd like to introduce the simulation result on the cloud seeding and the changing wind speed near the surface. So one of the methodological approach, so Professor Yoshida is investigating in the intervention in the cloud physics process by seeding. So he used scale sprinters, so which include several aerosol species and size, so which are adopted by the dynamics part, and aerosol cloud interaction is considered. So using this model, so they put the target radius for seeding while tracking the typhoon. And to mimic a seeding, so seeding was only the convective area, and the sulfate was added to the grid point. And multiple experiments are conducted in the several cases by changing the seeding location, such as IO or such as outer rain bands. So here is a result of the seeding experiment. So these figures show the time series of the central typhoon, central minimum sea level pressure, and 100 kilometers radius area average precipitation from the various cases. So black curve represented the simulation result without seeding, so named control. So compared to the, so here these curves show the intervention period. So we started the intervention at when the typhoon started to intensify. So compared to the control, the seeding within the outer rain band enhanced the decrease in the central pressure, so with the precipitation increasing. So we varied the seeding amount tested, but both scenarios have the same result. On the other hand, seeding within the IO and suppress the decrease in the central pressure, so with the precipitation decreasing, weakening. So this figure shows the pressure change of the typhoon, the central pressure, relative to the amount of the interventions. So when the seeding in the IO, so blue dots, so no change occur with a small seeding amount, but as the seeding amount increased, the typhoon weakening. So amount of the seeding used several million tons, so which is very, very huge, quite large, and not feasible for human intervention. So moving forward, in collaboration with a mathematical approach, so we need to focus on applying the seeding where or when it can be truly effective. And so the scientific approach, a scientific mechanism, so why the outer rainbow seeding enhance cyclone intensity or so opposite, so is not understood. So they are currently investigating. So please refer to the poster session. So there will be his presentation, his research. So another methodological approach, so I'd like to introduce a simulation result on the waking wind near surface. So this intervention is not aimed at reducing the intensity, typhoon intensity, but rather focus on the reducing the storm surge from the disaster prevention perspectives. So we represent the atmospheric field using the atmospheric model and the storm surge simulated by the storm surge model with a horizontal resolution 100 meters. And we use the real typhoon case that caused a 1 meter storm surge in Tokyo Bay, causing a serious damage. So this figure shows a simulated maximum storm surge, and this figure shows a time series of the storm surge at Tokyo here. So consistent with the observation as shown in the black curve, a 1 meter storm surge was successfully reproduced as shown in the red curve. So we conducted the numerical experiment to investigate how storm surge was reduced when the surface wind actually weakened. So we refer it as a Bay windbreak experiment. In this experiment, at the entrance of the Uraga Channel in Tokyo Bay, as shown in the yellow color, spanning the 16 kilometers east-west, so we actually modified the friction coefficient. As a part of our sensitive experiment, we conducted 25 experiments. We varied friction coefficient from the 0.005 up to 0.025, and north-south intervention from 2 up to 18 kilometers. So here's the result of the Bay windbreak experiment. So this figure shows the surface wind speed from the control experiment. So Typhoon center is located here, and we can see the cyclonic circulation with the maximum wind speed about 45 meters per second. And here is a difference in the surface wind speed between control and Bay wind experiment. So the wind speed has reduced up to the 20 meters per second in the intervened area and extend in the leeward direction. So this figure shows the difference of the maximum storm surge height between the control and experiments. So compared to the control, maximum reduction in the storm surge reached up to the 0.5 meters in here. So this figure shows time series of the storm surge at Tokyo, and this figure shows change in the maximum reduction in storm surge at Tokyo relative to the intervention amount. So as the amount of the intervention increased like this, so magnitude of the storm surge reduction gradually increased. So based on the result of the Bay block experiment, so engineering approach is investigated what increase the drag coherence can be achieved. So, and they are proposing the use of the windbreak nets. So windbreak nets are stretched east to west across the Uraga Channel. The cost of these nets is estimated here. And also, so we have estimated the overall cost to be the range of the several billion yen, Japanese yen. And also here is a impact assessment. Impact assessment is estimating the damage by the damage function at Tokyo. So due to the non-linear nature of the damage function, the reduction in the storm surge height up to the 0.25 meters, so resulting in the 10 billion Japanese yen, about a 32% decrease in the damage cost. So this figure shows the benefits cost in monetary units as vertical axis, so relative to the storm surge reduction horizontal axis. So vertical axis displays a decrease in the loss as a benefit and include the cost plotted inversely. So to increase the storm surge reduction, so costs are required, accompanied by an increase in the benefits. So once the storm surge reduction exceeds 0.1 meters, the benefit tend to outweigh the cost. And so LC is investigating the social demand, challenges, and roadmap for implementing the intervention methods for typhoons. So this is a Bay windbreak experiment scenarios. So they are considering the 4 scenarios aimed at the social implementation of the windbreak nets. So they are the Bay windbreak experiment is assessed as a high effect because it increases the maximum operations benefit. And so the need of the legal adjustment remains unclear and depends on the impact on the third party. However, but evaluation of the Bay wind experiments focused not just on the typhoon mitigation, but especially on the disaster prevention for certain ports. Okay, conclusion. So we are being composed of the various approaches, meteorological, engineering, mathematical, and impact assessment, LC. So we are working together to search for economical, viable, practical, and effective method of the typhoon control. So today I introduce the cloud seeding and the Bay windbreak experiment. And so based on the impact assessment, so if the slight reduction in the typhoon strength or storm surge can result in the significant damage reduction. So engineering approach is exploring what kind of the intervention device are available and their associated costs. But this is challenging due to the nature of the intervene in typhoons. So LC is investigating how to implement these engineering-based devices into society, so using the scenario-based approach. So windbreak nets I introduced today are relatively inexpensive and easy to implement. So meteorological approach, the challenge remains where the various techniques can be scaled down to feasible intervention levels. So to address these issues, a mathematical approach is investigating to identify the most effective timing and location for interventions. So 5th year milestone of this project, so we will identify the feasible intervention method to mitigate typhoon damage to a level acceptable to society. And we will start manufacturing the control device based on the specified intervention method. Okay, so here is so members of our team will be presenting the upcoming poster session. So for more detail about my presentation today, so please refer to these posters. That's it. Thank you so much.